Hello, faithful followers. We're going to talk today about finding the center of mass of what I call a half hula hoop. So this is a wire bent into a half circle. All right. Now, finding the center of mass. Well, because this object is symmetrical about this axis, we can infer that the center of mass lies along that axis. Clearly, there's the same amount of stuff down here and up here. All right, so the question is, how far along this dimension does the center of mass lie? Well, that's our exercise. And we're going to name that location from a location right here at the center of that, at the center of the whole circle, or the half circle. Well, what's our approach? Our approach is to say, where is the x-coordinate of the center of mass? Well, by definition, if we're not talking about a discrete set of point masses, what we have to do is say, let's look at the location of every little part of this and multiply that by where it is, its position relative to our chosen origin, and then divide by the whole mass. What we're really saying is we can find the position of the center of mass by adding up all the product of position and masses, and then dividing by the sum of all those masses. Well, these aren't discrete individual objects at places. What they are a collection of little tiny objects, each at a place. So what we turn this sum of discrete things into is an integral of, well, the position of each infinitely small element of mass, but still divided by the whole mass. All right? So, yeah, that's when we have extended bodies, continuous objects, we need to use this integral to add up all of the little parts. Okay, so let's just make sure we know what things mean here. So, what I like to do when I solve these problems is say, what do I mean by dm? What is my dm? Well, my dm, a dm is a tiny little bit of mass. So, like, right there, that little black object inside those two red lines, that's my dm. That is what I'm calling my element of mass. That part, that infinitely small part of the wire. All right? And so, well, let's see, where is that? Well, that's what this x refers to. So this x refers to the x coordinate of each dm. All right, well, the x-coordinate of this dm is right here. This is it. This is my x for that dm. Well, what you might be able to tell is that we can locate that dm by looking at the angle that that radius makes with the horizontal. Let's call this theta. So maybe you can tell that this x is r cos theta. Fair enough? So that's the x-coordinate of my dm. So that means that we can now write this in this case as, I'll jump down here, as our x-coordinate of center of mass is r cos theta dm. And I'm going to take the 1 over m and pull it out here. All right? This is a constant. It doesn't get integrated. We can pull it out in front of the integral, no problem. Actually, we can do the same thing with r. R is a constant. That doesn't get integrated. We can pull it out of the integral if we want. We'll get there soon. But here's what we have. Here's a problem. Here's another dm down here. All right? And notice that's located at a very different angle relative to that x-axis. So theta is a thing that varies. Theta is a thing that varies, but we're trying to integrate with respect to a different variable. And you can't do that. All right? You can't integrate something that varies with respect to a different integral. Sorry, with respect to a different variable. So that means we've got to try to turn either, this theta into something in relation to m, or this dm into something that relates to theta. So how do we do that? Well, we do that by saying, how can we characterize our dm? Well, here's what I will say. This is a wire, all right? And so by definition, it has a linear density, lambda, that, well, by definition is mass per unit length. All right, there are area densities that I call sigma, most people call sigma, and that is defined as mass per unit area. There's, of course, our classic volumetric density, that's mass per unit volume. But since this thing doesn't have volume, it's infinitely thin in this dimension, and in the one perpendicular to the page, it's just literally one-dimensional. It's a line that's bent. All right, so it has a linear density that we call lambda. So, well, if the whole mass is, well, now we can express, actually, I go through this step. If the linear density is mass per unit length, then the whole thing has a mass lambda times L. Which means that my little tiny element of mass, how massive is that? Well, that depends. That depends on how dense the thing is, and, well, how long this tiny little, there's a dl, how long that tiny little section of the wire is. All right? So, now we can write this as r, 1 over m, r cos theta, well, lambda dl, but we still have variable and integrating with respect to a different variable, not good yet. So what can we do with dl? Well, let's notice that, here's a dl. This dl, for you geometry types, is actually a tiny little, what we call ds, a tiny little arc length. Yeah, arc length, right? So geometry says, how long is an arc? Well, that depends on a couple of things. It depends, how long is an arc? That depends. It depends on two things. It depends on, how far, what angle spans the arc. So here's a theta, and it depends on r. So we say that this s is r theta. So our dl, which is really a ds, is really an r times, a tiny, tiny little angle spanned by, let me try to clean up a touch here, spanned by this end of our dm and this end of our dm. Oh boy, that's not pretty. But this is a tiny little d theta angle, which, multiplied by that r gives us a tiny little ds. Now check this out. We can say now that dm is lambda dl, which is lambda ds, which is lambda r d theta. Ooh, d theta. Ooh, theta. Life is good. So now we can say that the position of center of mass is 1 over the whole mass times r cos theta times lambda times dl. dl r d theta. And look, we now have a constant, and a thing that varies, and integrating with respect to that variable. We can do that. All right, so I'm going to shrink a little bit and say that the position of our center of mass is 1 over m. Let's see. Let me pull out a couple of constants. All the stuff that's constant, the r, the lambda, I'm going to pull out. So we get the center of mass that gives me r squared lambda over m times the integral of cos theta d theta. Now, what does theta vary from? We need limits of integration. All right, theta varies from, notice we're measuring relative to this x-axis, right? Relative to this x-axis, and our first dm is down here, and our next or our last one is up here, and we're using a convention that when we name angles or measure angles, we measure them in that direction. All right, so notice we measure, our first one is there, our last one is here. So we are evaluating from negative pi over 2 to positive pi over 2. Some would say negative 90 degrees to positive 90 degrees. Okay? Now, the position of the center of mass is r squared lambda over m. Well, and for reasons that you can find elsewhere, it's not the world's most challenging thing, but the integral of cosine theta d theta by definition is sine theta. And we've got to evaluate that from negative pi over 2 to positive pi over 2. Right? Which means, to be real formal about this, this is r squared lambda over m times, well, we evaluate from the top value, pi over 2, and we subtract when we evaluate from the bottom value. And, well, the sine of pi over 2 is 1. The minus the sine of negative pi over 2 is negative 1. So this whole thing is 2. And so what we get is we get the position of center of mass is, well, again, this whole thing is 2. We get 2 r squared lambda over m. Now, what's lambda again? Well, lambda, let's see, 2r squared over m. Lambda is mass per unit length. So our masses go. What's the length of this half of a circle? Well, it's half of a circumference. So that means it's 2r squared. Let's see, the circumference of a circle is pi d. The length of a half a circle is pi r. And then a factor of r goes. And we have an answer. We have that the position of the center of mass of this half circle as measured from the center of the circle is 2 over pi times r. 2 over pi times r. 2 pi's. Yeah. 2 pi's. That's not a word. 2 pi's are my favorite way of saying it. That's the answer. All right, 2 pi's are. And that's independent of the density of this thing. Well, that's it. It doesn't matter what r is. R can be anything. The center of mass is, you know, what's 2 over pi? Well, it's 2 over 3.1. So it's, you know, 0.64, 0.6 something. It's less than 2 or 3.666. Right? So it's, you know, it's less than point. Yeah, sure. At least this is less than 1. It better darn well be, which means that the center of mass, you know, call that 0.6-ish. Measured from here, this whole, you know, this is r. So where's 2 pi's are? No, it's about there. That's what the center of mass of that object is. Fair enough? Now, soon, next time, we will apply this idea. We can apply this one and or our derivation of the center of mass location of a triangle to find the location, to find the location of the center of mass of a solid solid half pizza. So stay tuned. Farewell.